About 6 years ago, I first started to do my own research about this concept of compost heat recovery, and I put together a nonprofit research organization called compostpower.org, brought together a bunch of people who were much smarter than I am and brought expertise from compost science to engineering and renewable energy and permaculture together, and we did a whole bunch of projects and research experiments, in some cases in partnership with universities like the University of Vermont, University of New Hampshire, Amherst, Evergreen State College out in Washington, and over the years figured out several different ways to improve upon work that had been done back in the late 1970s in France by a gentleman named Jean Pain, who first came up with an idea of composting shredded woody material, basically wood chips, and generating hot water as well as methane. Jean Pain died early after his concept did get some publicity, and it seems like through the 1980s it kind of fell on the cultural back burner. So it's exciting to be part of reviving what really is not a new idea, but to bring it to a full spectrum of types of situations where it can work at the homestead scale or the large scale, depending on what kind of material you've got access to and what your heating and hot water needs are. Earlier this year, my book came out, The Compost-Powered Water Heater. It's full of case studies and project briefs, as well as science and history of the concept. I wrote this book partially because I wanted to put all of what we had learned into one guidebook for do-it-yourself projects, as well as a tool for people to plan farm scale or commercial scale projects. It's got a couple dozen different case study style briefs of different projects that we've done, and gets into a lot of the science and specifics of compost, everything from recipes and feedstock planning to expectations as far as the amount of heat you can capture per ton or cubic yard of material and for how long. Welcome you to get a copy. It's available in the ebook, Kindle, or printed versions in most bookstores and on Amazon, etc. As most of you probably know, well-managed compost piles do generate a lot of heat. You'll see temperatures inside an active pile anywhere from 120 to even up to 180 degrees. And probably you've wondered, there must be some ways I could capture that heat. And the trick is usually managing all the variables of compost. You need to have the right food for the microbes. You need to have a good recipe in terms of carbon and nitrogen materials that will yield a good quality compost product after it's through its process. The two trickiest variables to manage are moisture levels and the aeration. And so that's part of what we've been experimenting with, are different ways to manage those two particular variables. Here's a pile of a steaming windrow of active compost that we took at a compost site in Vermont last year. That steam is heat that's escaping that can be captured. In some cases, I've seen several examples. Actually, about a year ago, there was a goat dairy farm in Vermont that had been piling up their manure and bedding out in the field for years and not really managing it. They had a big fire. It took about 3 days for the fire department to put the fire out. If you've got a pile of biomass material, whether it's manure or wood chips or yard waste or anything else, if the pile is above a certain height and has the right combination of enough moisture for the microbes to be happy, but it dries out to the point where some of the material can burn, it will. Murphy's Law, and this happens quite often, actually. So another gentle signal from the universe that there's energy here that we could be harvesting. This is a shot of two different windrows, one that has just been turned to the left, and the other windrow to the right hasn't been turned in a week. So immediately after aerating material, which is typically done by tumbling or turning the material, the microbes kick into turbo mode and really go hot and get their thermophilic process going. The trouble with turned windrow types of compost process is usually within 2 days after the material has been tumbled or turned, it will start to go anaerobic. meaning there's not enough oxygen flowing through the pile to keep the microbes happy, that results in some other problems that can mean odor issues. It can mean that your goals of getting well-produced compost with pathogens and weed seeds killed is going to take longer because the pile cools off. It also generates methane when the piles go anaerobic. And as some of you may know, methane is a much more severe greenhouse gas than CO2. All these piles of slightly anaerobic or entirely anaerobic material sitting around or in liquid manure pools or even sewage treatment plants, landfills, all these unmanaged biomass systems are generating tons and tons of methane that isn't in most cases being captured for any productive use and ends up just being a very obnoxious greenhouse gas that comes along with all kinds of other odors. Well-managed compost that's properly aerated does not generate any methane, and it also has very minimal odor issues due to the aeration process and the proper mixture of materials. Typically, a commercial compost site with food scraps and yard waste or maybe some manure as their materials you'll see active hot pile temps for up to 2 months on one batch of material. This is a shot of one of our early attempts at replicating Jean Paine's wood chip mound with water lines coiled throughout the material through compost power and classes that I teach at Yestermore Design Build School in Vermont. We've learned a lot since then. It turned out that this particular pile, you can notice, has a reddish tint to the material. This was hemlock, which is highly rot resistant. And so we didn't get good pile temps on this particular project. Learned the hard way that certain types of wood materials don't rot, and as we say, no rot, no hot. A couple of the key variables to understand when you're thinking about compost. There's feedstock variables. What kind of material are you composting? It is possible to get hot thermophilic active compost piles without adding a lot of nitrogen. Just wood chips alone will cook and eventually turn into decent compost over time. But typically you want a good mix of usually about 50% material being a carbon source and 50% being a wet, heavy nitrogen kind of source, such as food scraps or manure. Those materials need to be blended well together so that air can pass through the material, and they also need enough moisture. You need anywhere from 45 to 65% moisture content for the thermophilic microbes that generate heat to stay happy. So one of the issues to manage with compost in general is humidity levels of the material. If it dries out too quickly, you won't continue the thermophilic process and it will take a lot longer to make a good compost product. If it's too wet, then there won't be ability for air to pass through the material, and you'll have the same kind of issues where it starts to go anaerobic and you're not killing pathogens and weed seeds, you're not getting good decomposition, and you're also likely getting lots of obnoxious odors. So the feedstock variables, the water, and the oxygen variables are the key sort of things to manage. What comes out of a compost pile is water vapor and steam as it dries out, heat, CO2 emissions from the natural breakdown process, and a finished product of a good soil amendment if it's done properly. Passive aeration refers to composting piles that have enough height to them so that there can be somewhat of a chimney effect where air will naturally move up through the pile due to the heat that is typically generated in the top center. Windrows can be good passive aeration systems depending on the feedstock and how well mixed the material is. So if it's got enough carbon materials such as wood chips or yard waste, then air can move through the material without active tumbling and turning or other means. That's the key to the Jean Paine method. A very fine textured bark mulch kind of consistency of wood chips piled up, soaked with lots of water, will have a nice passive aeration effect where air can move up through the pile. We have amended the Jean Paine method to also put aeration pipes under the material before we build the pile. That allows additional air to get under the mound, and the chimney effect can bring that air up through the whole pile. A Jean Pain style pile of wood chips with water lines coiled in it can stay above 110 degrees for up to 18 months, even through winter temperatures. So that material takes a long time to break down, but it's got a lot of heat that can be captured for that whole process. Windrow turning equipment. There's a lot of different options out there that farms and commercial scale compost sites are using. Some of these pieces are PTO driven tractor style turners. Others are self-propelled, very expensive machines that rage through these windrows and turn them very quickly. This method of compost production has got a lot of history to it. It's typically how most people think about doing compost production at scale. However, in the last 10 years or more, there's been a lot of new, more improved methods of managing the aeration of the material, where fans are laid underneath the material and air is pushed or pulled through the material by the fan instead of by all this mechanical turning and tumbling. This is a couple of pictures of an aerated static pile compost system. Aerated static pile means that you are not constantly tumbling and stirring the material. In most cases, this is done with what is known as positive aeration, where you have a blower attached to pipes, and there's a timer, and the blower turns on and off, typically in 15 to 20-minute bursts, and then rests for about that same amount of time, depending on the material, and it blows air up through the pile. This is a pretty simple way to manage the aeration without having to turn it and tumble it every week. Most commercial compost sites that are using this method will still do 1 or 2 tumbles of the material to make sure that the material on the outer edges gets mixed in to the central core, where you get the nice hot temperatures to kill the pathogens and weed seeds. The process for further reduction of pathogens, PFRP as the compost standard, requires that you've got temperatures above 132 degrees for at least a week in order to kill pathogens and weed seeds. Here's a little diagram showing how positive aeration works. It's pretty simple. Air is blown up. One of the challenges with positive aeration, however, is that the inner core of the pile can tend to dry out too soon, and it's very difficult to reintroduce moisture inside the pile without tumbling it and adding water. Another issue with positive aeration is that it's blowing air up through the pile, which tends to blow odors up into the wind, which may disturb neighbors depending on where your site is located. Odor control is a very big deal in commercial composting, and one of the biggest roadblocks to commercial compost being a rapidly growing category. It is growing rapidly, but there's been lots of sites that have been shut down or put through some major obstacles due to odor issues being a big problem to neighboring communities. So in any commercial compost site plan, in almost every case, how to control and ensure odors are not a problem is one of the biggest questions. And it's a big problem, really. So what we've noticed is the other method of aerated static pile composting is called negative aeration. It's basically just turning that fan around, and instead of blowing air up, you're pulling air down through the pile. There are some other considerations that need to be made when you're doing negative aeration, because you get a lot of condensate and leachate, water coming through those pipes that can tend to clog up the pipes. So you need to have ways to capture the condensate, which is known as a condensate trap. And those can be simply ways that there's little chambers in the system where that water can accumulate and then be pumped back out. In some cases, a plunger valve can be automatically set up so that water is pumped back out right on top of the pile. It's not a difficult thing to manage, but there have been people who've done negative aerated systems and without realizing that they needed to do this, and then their aeration pipes would constantly get clogged up with water and the air would stop flowing. If you do it right, you'll get great temperatures and a very rapid process from a compost production timeline, as well as the ability to control and capture odors. With negative aeration, you're sucking air down through the pile. That means you're not blowing odors up into the wind. After that air is pulled out of the pile, it can be vented into what's known as a biofilter, which in most cases is simply a pile of wood chips, or another section next to the compost pile where perforated pipes let that compost air out into a bed of wood chips or other material that will absorb the odors from the compost. One of the tricks with biofilters, however, is when you're venting 150-degree supersaturated wet hot air into a biofilter, it can very quickly in some cases become saturated with moisture, and that's a point where it can fail and the odor capture properties will no longer be working. So one of the advantages we've come across by accident really is that when you pull most of that heat out of that air before you vent it into the biofilter, you enable the biofilter to last much longer and to be much smaller. We've got one example of a project where we're capturing heat out of that compost air and then venting the smelly compost air directly into a biofilter in a greenhouse. And actually the biofilter is the seed beds of the greenhouse themselves have about 1.5 feet wide and 1.5 feet tall layer of compost on top of perforated pipes, and that's all under the soil in the greenhouse. So the greenhouse serves as a biofilter in this sense. The seed beds stay at 70 degrees through the winter in Vermont, and all the CO2 emissions from the compost end up in the greenhouse, which feeds the plants, which has a dramatic impact on the amount of fresh air that needs to be brought into the greenhouse, which reduces the amount of heat that you need to keep that greenhouse warm in winter temperatures. So that's a very interesting thing that we've realized in terms of heat recovery, odor control, and CO2, that all can be turned into positives. This shot here is just a bunch of different temp gauge sensors that we took on a pile. This was done by Highfield Center for Composting in Vermont, one of our research partners. Shows you the range of temperatures you'll get in a typical pile. The lower temps represent spots where there is not good blending of the material, where you've got a dense clump that air cannot pass through. Generally, the higher in the pile you go, the higher the temps, because you get more thermal mass and buildup of heat in the material. Here's a shot of Jean Pain, a farmer in France who is known as one of the original tinkerers of compost heat recovery. He did a bunch of very interesting projects with wood chips, clearing undergrowth in the forest to prevent wildfires, and then composting it to make soil for his farm. He was one of the first people that showed that you can make a good quality compost with wood as your only input. And there is some nitrogen in wood chips, especially bark mulch from the bark, but it's not much nitrogen in general, not a typical compost recipe. And what he found, and which was validated through the Jean Pain Institute, through some scientists in Belgium, is a hypothesis that I don't know if it's been completely proven, but at least partially proven. The microbes are breathing air, and one of the biggest components of air is actually nitrogen. So what ends up happening is the microbes do their thing, some of that nitrogen from the air gets fixed into the compost. So he would end up with a very good carbon to nitrogen ratio in his finished compost with wood as his only input. He also built his own little anaerobic digester tanks that he would place inside the mound of wood chips. The wood chips would be passively composting, and that would keep the digester at the right temperature, which needs to be around 100 degrees. He filled the digester with just water and partially composted wood chips and would get 5 months of steady daily production of methane through a simple tube in the top of the tank, and he would use a compressor to pump that into tractor tire inner tubes to store the natural gas. He ran all of his trucks and tractors and generators on that natural gas and met all of his household hot water and heating needs with hot water from the water lines that were buried in his piles of wood chips. This is a screenshot of a video. If you search YouTube for Jean Pain, you'll find about a 20-minute documentary that was made about him. It's not the best quality film, but it's a really interesting story. This is a shot of one of his very large 80 cubic meter pile of wood chips that he would generate hot water for 16 to 18 months just by circulating water through the pipes in the pile. and then he would tear it down and build a new one. One of the main pioneers of this concept that kept the Jean Pain method alive in the 80s is a friend of mine named Bruce Fulford, who is in Boston these days running City Soil Greenhouse. He was working with the New Alchemy Institute to build what I believe was the first compost-heated greenhouse in the U.S. at least, at a project through the New Alchemy Institute. This is a shot of the greenhouse. The north wall had a chamber, about a 6-foot by 6-foot chamber with lots of openings you can see through the outside of the greenhouse, where he would load in chicken litter, food scraps, and yard waste that were mixed together. And he had fans blowing air up through those piles up into the greenhouse to keep the process active, and it worked. He kept the greenhouse warm enough to keep tomatoes growing through the winter on Cape Cod. The only problem was the odor issues in the greenhouse made it nearly impossible for humans to spend more than a couple of minutes in the greenhouse. So it worked in one sense, but it also proved or showed one of the main challenges with using hot air pulled out of compost for space heating is the odor issues. Unfortunately, the greenhouse wasn't built very well, and I think 3 years later it started to fall apart, and Bruce moved on to other projects, but he did show one of the things as far as how this can be approached. This is a shot of a modified Jean Pain style mound that I helped to build at Evergreen State College a couple of years ago. I believe this is the first case of a college dormitory building being heated through a winter climate entirely with water, hot water generated from compost. They have radiant floor heating in this 6-unit dorm building next to this pile. This was a mixture of about 60% wood chips from pine, 30% sawdust from alder, and about 10% horse manure that was all blended together. About 40 cubic yards total, and I think it's about 12 feet in diameter. We laid out perforated pipes underneath the material and then built this hay bale wall around it as we went up. The hay bales help contain moisture, they help insulate, and they also, actually these were straw bales, they also add their own heat to the system as they break down as long as they're wet enough. We had, I think, 600 feet of PEX tubing coiled across 5 or 6 layers. The cinder blocks you see are just used to temporarily hold the pipes down while we cover them with fresh material and soak that material with water, and then the blocks get pulled out and we do another layer. This is a similar project that I did at an eco-village in Chile about 2 years ago. That was for an off-grid guest house. It was a gravity-fed water line coming in and hot water system for just wash water on site. Very similar approach. This is a shot of the Jean Pain style system that we did in Vermont. This is Ben Falk of Whole Systems Design, a very innovative leading voice of permaculture practice in Vermont and elsewhere. Built his own Jean Pain pile and used it to provide hot water for his raised beds in his greenhouse, and was testing it with a makeshift hot tub just after we got a 3-foot snowstorm in the middle of winter to show that it would work regardless of the climate. Here's a shot of a UVM project we did to heat the Slade greenhouse a few years ago. A similar one in Norway. And here's a drawing of a different way to do the Jean Pain method, where we coiled the water lines, the heat exchange tubing, onto what's known as cattle panels, basically sections of fencing that were 12 feet by 4 feet. I think we got about 150 feet of water lines on each of those cattle panels, zip tied them in place so that the beginning and end of each loop it was in approximately the same spot. As we built the pile, we would just throw another layer of this cattle panel heat exchanger on, and then we connected them all together on one end. This made it really easy to tear the pile down a year later. We just disconnected along one side all the water lines and then just drag out the panels one by one. You'll also notice the aeration tubing shown underneath that lets air get under the material to keep the passive aeration chimney effect process going, to keep the bark mulch that we used in the thermophilic hot stage. They use this hot water to keep the radiant slab in the building next to it warm in a radiant floor heating system. That was actually a vermicomposting, worm casting room that they had set up, and this was used to keep that warm process going through the winter months without needing any other energy source. This is another very interesting tinkerer, Conan Eaton of Auburn Star Farm in Vermont. He basically built, with some help from Compost Power and Highfields, an insulated shed that has aeration channels built into the floor and water lines zip tied to the rafters in the ceiling. It's a 12-inch thick, very well insulated shed, and the aeration system just blows air up through the channels in the floor, blowing that hot air through, keeping his manure composting active and hot, and then water is circulated through the pipes in the ceiling to capture that heat, and then he used that hot water to heat a couple of very large equipment sheds and buildings next door, and he actually just used old tractor radiators with window box fans placed behind them, blowing that hot air from the hot water into the building. Very simple in terms of how the mechanics of this work. Not exactly an efficient way of capturing the heat, but it works, and it's efficient from his point of view because he can very easily load up this shed with his tractor, and then 2 months later, or maybe about 10 weeks later, unload it and fill it up again, and making compost without having any issues in terms of controlling the variables, because all the moisture is contained in the chamber. So he didn't get material that would dry out too quickly, and he was able to continue operating this for the last couple of winters, heating a lot of space without any cost. This is a diagram showing the AgriLab active aeration system at the University of New Hampshire. So this shows how the negative aeration process is used. Air is pulled down through the compost that's in a covered building to control the variables of moisture, and that hot air is pulled through the isobar heat exchange system, which condenses the moisture in that hot vapor and converts that energy into a large water tank, keeping a large tank of water hot, which they use for facility heating and wash water. You'll notice that there are condensate pumps and traps built into the system so that as moisture builds up and is collected, it can be captured and reintroduced into the compost and prevented from blocking the aeration channels themselves. In concept, this is pretty simple. The practical application of this approach does involve some construction, and some very important details need to be tended to in terms of how the aeration system is built. The blower fan that does the work here is not a high amount of energy, but it does need to be a robust fan, depending on the size of the pile, to be able to move enough air through the material. Typically, the blower fans are on either 15 or 20-minute timer cycles, where one zone under the compost is aerated at a time, and then it switches to a separate zone. So there's always at least one zone of compost being actively aerated. That means there's always heat being brought into the system, so there's a base load of energy coming into the water tank. So you've got reliable 24/7 hot water supply, and the compost doesn't need to be aerated constantly. It needs time to rest. If you over-aerate it, you can cool the pile down too much and disrupt the thermophilic process that you want. Here are some shots of an isobar array. They're basically just stainless steel heat exchange tubes. They have a separate tube on the inside that has a refrigerant in between the layers. The refrigerant boils at a low temperature, and the tubes themselves are on an angle. So inside these tubes, you've got a boiling vapor condensation cycle going on, which passively sends the heat up the tubes to the other end where the water tank can collect that heat. So there's no water pumps or any mechanical system involved in this heat exchanger other than the fan that is moving the hot, wet air from the compost across the isobar pipes. Here's a planning drawing of an aerated compost production bunker that was done through Highfields Center for Composting, showing the aeration channels and how the concrete was poured, as well as the spacing and the angles in the three-wall bunker. They have a roof over this building, again, to keep too much rain or snow from overly watering the material, but there was no there were no walls to this facility, just an open 3-wall bunker that could be easily loaded with a typical tractor. Here's a planning drawing of the biofilter in the seed beds at the Jasper Hill Farm, one of the projects that has an isobar AgriLab aeration heat exchange system. So this is where after the heat is pulled out of that air, again, the air starts out anywhere from 140 to 160 degrees. After it's gone through the heat exchanger, most of the heat has been captured from the air. The air is still 60 to 80 degrees usually, and it's vented again with the same fan doing all the work. Just the exhaust of the aeration system after the heat exchanger connects to pipes that go into perforated pipes that are under the seed beds. So the seed beds are basically always getting a very mild amount of warm air coming into them. They measured the temperature of their seed beds throughout both of the last winters, and they were nearly always right at 70 degrees through the winter. And then all the CO2 from the compost ends up in the greenhouse. They did notice at the end of their second winter, which was last year, that there was a beginning of a slight odor of ammonia in the greenhouse, which was their indication that the biofilter had been saturated. So they just dug up the seed beds, removed that compost, blended that into their other compost, and reloaded the biofilter chamber with finished compost to be the biofilter for what they expect will be another 2 years. The first active negative aeration and heat exchange system that was ever built was actually done in 2007 at a farm in Vermont called Diamond Hill Custom Heifers. They're basically a boarding school for calves that are raised and kept in a controlled and clean and warm environment until they're up to a certain size when they go back to their farm where they came from. You'll notice a lot of people collaborated on this project, including Bruce Fulford, AgriLab Technologies. It was a very innovative first run at how to do this. It received the Governor's Environmental Award for Excellence in Vermont a few years later. So for the past 7 years, they only operate this in winter months. It's a 200-ton system in a shed like this. They've been getting 200,000 BTUs per hour, 24/7, from this 200-ton pile of manure and bedding. The average reliable, consistent rate we've seen in terms of the amount of heat you can get with this negative aeration heat exchange system is 1,000 BTUs per hour per ton of material. And that's typically over a 6 to 8 week period per batch when you're talking about manure-based compost feedstocks. With food waste and yard waste and forest residue blends, it's likely that you'd get a longer run or hotter temperature compared to manure. With woody material, it takes a lot longer to break down. So there's some variables that would make the 1,000 BTUs per hour per ton go up to 1,500 BTUs per hour per ton. But in general, we see an approximate total of about 1 million BTUs captured over a 6-week period per ton of material in the active aeration process. 1 million BTUs is worth up to $30 depending on how you are getting your energy for heat and hot water now. The price of good quality compost can range from $30 to $100 per ton depending on how it's sold. So the heat value, the value of the heat and energy that can be captured, in essence doubles the economics of composting in general, which is a pretty big deal. Another way to think about it is the cost per ton for coal is $30. So you can get the same amount of energy value as you can from coal without a coal mine, without burning anything, and while making great quality soil, all without any emissions, and while solving environmental pollution issues that come from other ways that these biomass waste materials are mismanaged. Raw manure spread on fields, almost all it ends up in the rivers and causes all kinds of phosphorus and nitrogen runoff issues. Sewage treatment plants dilute that water before they pump it into our rivers and lakes. But right now in the U.S., there's more than 1 billion tons of animal manure and human manure produced each year, 1 billion tons. And most of it ends up in our waterways or used as fertility that's full of pathogens because it's not composted first. So well-composted manure is a huge opportunity, both from a building soil, watershed health, and energy self-reliance point of view that is very, very interesting. I used to, growing up in Vermont, there's all these liquid manure farms, and they're spreading their raw liquid manure everywhere. It's not only a nasty odor that spreads for miles, but it's a really big pollution problem. And so I'm really excited to have found a way to offer a better way to manage manure and turn it into healthy soil and combustion-free energy as a way that farmers will actually make money or save money compared to how they're doing it now with these trucks spending lots of money on fuel to truck around all this water in these liquid manure systems. The other really big thing for farms, animal farms, a couple of our projects are now using the composted animal manure as their main bedding input in the barn. One of our projects is saving $80,000 a year because they're not buying truckloads of wood chips and sawdust anymore. They're using their recycled composted manure as their main bedding. Bedding needs to be pathogen-free, soft, and absorbent, and compost is all of those things. So that's another really interesting financial angle for animal farms in general. It's not widely known, but there's been a bunch of studies from Cornell and University of Vermont that have proven that the pathogen count and herd health issues with using composted manure are actually better than using sawdust. I want to go back here to this slide. This shows the Sunset View Farm compost heat recovery project that was built in 2010. The aeration channels in the floor, you can almost see there's a bunch of little holes. So those are channels that are cast into the concrete, and then sheets of plywood are cut to the right width, and a bunch of holes are drilled in the plywood. Before the manure material is spread out and loaded up into this bunker, there's about a 4-inch layer of wood chips that's spread out on top of these aeration channels. That helps to distribute the air and keep the channels from clogging up. It also acts as the beginnings of a biofilter that'll start to absorb odors as air is pulled down through the pile. Here are a couple of other shots of isobar heat exchange arrays. The two on the left are the original versions of these long linear pipe chambers. The first one at Diamond Hill Farm was 60 feet long. It had to be custom fabricated on site because of that, and was very expensive compared to the one on the right is a system that has the same capacity up to 200,000 BTUs per hour from a 200-ton system, but it's only about 7 feet wide and 8 feet long in total, including the water tank. We figured out a way to manage the vapor flow with much less volume of heat exchange pipes. Here are the shots of the aeration ductwork coming out of the back of the compost production bunker at Jasper Hill Farm in Greensboro, Vermont. And on the right is their isobar heat exchange array. On the top of the picture on the right, you can see the big pipe coming in with the elbow. That's leading to the aeration fan. So that fan is doing all the aeration work, pulling air out through each of the compost zones and pumping that hot, wet air through the heat exchanger. This is a shot of Jasper Hill Farms, one of the most innovative and sustainable dairy farms I've ever heard of. They also have an on-site anaerobic digester, and the compost heat recovery system is providing the hot water to keep the digester at that 100-degree operating temperature for the digester. The liquid coming out of their digester is flowed through a small living machine, basically a series of constructed wetlands that are actually in the greenhouse. So by the time that water leaves the greenhouse, it is perfectly clean. And so they're managing all of their nutrients, keeping them on site, and have really nothing obnoxious, no odors. The place is beautiful. They make some of the best cheese on the planet. and they're almost entirely self-reliant in terms of energy. That system was installed in, like I already gave you this quick overview of Jasper Hill. Sunset View Farm, their isobar aeration and heat exchange system cost about $80,000. The building that the compost is produced in, I believe, cost about the same amount. But they're saving more than $100,000 a year in terms of the energy and the value of bedding replacement compared to what they were doing before. So systems like that can pay for themselves quickly if they're done right. Here's a screenshot of a Cornell Waste Management Institute report about using composted manure and dairy separated solids for bedding. And anyone who would like to see that full report, happy to provide it. It's a very interesting report that goes through all of the pathogen issues with various forms of animal bedding. So the latest innovation we've been working on for the last year has been to take the active aeration isobar heat exchange system and condense it, make it smaller, make it cheaper, and make it mobile. So we built what we call the Compost Heat Wagon. It's based into a typical cargo trailer with all the aeration data monitoring, keeping track of the compost temperatures and water temperatures, timing systems to control the way the fan operates, and the heat exchanger. And we've actually got this first prototype up and running at Vermont Compost in Montpelier, Vermont, probably one of the most well-regarded organic compost companies in the country. And right now it's heating a greenhouse. And basically the way this works is just like the other negative aeration systems. The 4 inlet pipes on the side of the compost heat wagon are connected to different zones underneath a pile of fresh compost material. The system pulls air through each zone in a rotation and keeps the water tank full of 120 to 140 degree water. The exhaust, after the heat's pulled out of that air, in some cases can be sent right into a biofilter in the greenhouse. In the case at Vermont Compost, we actually send the exhaust back into a perforated pipe that's buried in the top of the compost pile so that the moisture is reintroduced to the compost. Because he did not need extra heat or the CO2 in his greenhouse because he already has a whole bunch of chickens living in his greenhouse. Anyway, this system is really interesting in my opinion because it's very compact and we can get this up and running in a matter of days without any permanent infrastructure or buildings being built. And it's also very easy to finance. We've found 2 banks that have approved lease-to-own programs on this, so people can get up and running with very little to no cash investment up front. This system can capture anywhere from $30,000 to $50,000 in heat energy per year and pay for itself within a year or 2, depending on how it's set up. Here's some shots that were taken just last week. We rebuilt the compost pile and loaded it with fresh material. It's full on winter in Vermont. We had 25 below. The system is still working, even though the compost piles are covered in snow and there's nothing containing the compost to help insulate it. The pile is very large, and the aeration pipes you can see on the right, they're laid out, and some woody material, bark mulch, is spread on those pipes first before the blend of food scraps and manure is piled up on top of it. The first week we had this set up, the pile temperatures were 175 degrees roughly, very hot, lots of heat. On the picture on the right you can see how we built an aeration, a temporary aeration system before the compost was spread out on top of it. These perforated pipes are protected by 2x8 planks so that the bucket loader can scrape the material out and drive through in between, straddling these pipes without crushing them when the pile is rebuilt every 4 to 6 weeks. There's a shot on the upper left of the compost heat wagon next to the greenhouse and the beginnings of the compost pile next to it that's connected through the aeration pipes. The lower left you can see the isobar heat exchange vapor box. So those white panels are actually baffles that force the air to zigzag back and forth across the heat exchange pipes. The fan is in the center top of the picture. The green box on top is pulling the air through the compost, through the heat exchanger, and then out through the ventilation pipe. The picture on the right is Carl Hammer of Vermont Compost testing the heat coming out of the exhaust pipe from the compost heat wagon. So I think trying to boil down, the basic simplicity of this idea, you're managing the aeration, which is critical, without needing lots of diesel fuel to tumble and turn and heavy equipment. That's been using active aeration, aerated static piles has been shown to be about 25% of the energy input required compared to using windrow turners or tractors to tumble the material mechanically. So by itself, aerated static pile composting is almost a no-brainer in terms of energy. When you do it in this method, it gives you the ability to capture odors and heat and CO2. It also allows you to have some very good space efficiency in terms of how the compost is managed. If you have a turned windrow operation, you need space between each windrow for your equipment to drive up and down. When you've got a 200-ton bunker that's 30 feet by 30 feet with material piled 6 to 8 feet tall, you can get about 3 times as much material in the same amount of land space compared to windrow composting. I mentioned that we get about 1 million BTUs per ton. With the Jean Pain method, it's about half that. However, it's for a much longer period of time. So if you're getting 500 BTUs per hour per ton in a Jean Pain system just by running a circulation pump of water through the pipes in the pile of wood chips, you can get steady heat for 12 months off of one pile if it's done with the right texture and the aeration is done properly. That is close to the same amount. If you add that up 12 months at 500 BTUs per hour per ton, it ends up being almost as much energy overall as if you had just burned the wood chips. So it's very interesting to think about the idea that you can get just about the same amount or almost as much energy from compost heat recovery as you could from burning the material. That's something that most people think can't be true, but I assure you that it is from our measurements. Another way I think about this, I mentioned already that there's more than 1 billion tons of material generated in the U.S. alone each year in terms of manure. Right now, 35, or I think last year it was down to 34 million tons of food scraps generated in the U.S., and 95% of that is still going into landfills. So not only is that a huge expense to haul all this nutrients away from our farmland, but it's filling up landfills, causing lots of environmental issues, lots of cost problems, and we're throwing these nutrients away. This is a huge soil loss issue in general that we're facing and around the globe, and we need to feed our soil instead of dumping all of our nutrients into landfills and into waterways. So this concept of aerating compost and capturing heat and making a really strong economics case for municipal compost sites, sewage treatment plants, farms, greenhouse operators, this is all a way for us to make the economics of compost so compelling that we will stop using this material in ways that ends up being a pollution and turn it into what it really is, which is a nutrient resource and an energy resource. Hundreds of thousands of sites across the U.S. can have very, very compelling economics around that, regardless of whether or not they care about environmental issues or not. And my background is in renewable energy. I was in solar power for a few years and lots of nonprofit activism around sustainability. And I'm excited because this is a concept that will make economic sense for people who don't need to even care about environmental issues for them to see, oh wow, yeah, I guess waste is a stupid idea. Maybe I should convert that to something that is valuable to me and others. And so I feel like this is a really big picture, exciting opportunity in general, and something that I hope you will all share with your friends and neighbors as far as a way for them to convert a material that has a high economic and ecological cost of disposal and turn it into something that's got a ton of value for the soil and for their energy in terms of their pocketbook. Here's a quick rundown of the investment costs of doing an isobar AgriLab active aeration system for a brand new site. We're actually looking at this project, which is for a large zoo. Right now, the zoo is spending $30,000 a year to haul away their zoo poo or their animal manure. This is just a quick list of infrastructure for a new compost facility in a covered room with an aerated pad, concrete pad, that they will use the heat recovered from this to keep 2 large greenhouses operating through the winter. So the cost of all of this, the concrete, the compost heat wagon, labor, plumbing, ductwork, etc., it adds up to a pretty big number, depending on your perspective, about $250,000. If they didn't need to buy a new manure mixer spreader or a loader, which most farms already have that kind of equipment that they would need, and if they went without the pole barn covered structure and just did it in the open air, which would see a little bit of reduction in the amount of heat they could capture, but it would still work without the covered structure, then it would have been about $100,000 of investment. The compost heat wagon can be financed, so that's not necessarily cash up front, but a quick rundown of the potential upfront costs. And here is a preview of their annual operating costs and savings. So labor and costs to manage the compost site, and savings in terms of energy, the value of the compost they can sell. What isn't factored here is the value of the food they'll produce in the greenhouse, which will go to the animals in the zoo. A couple of these zoos, or this particular zoo, has a few manatees that eat about a dump truck load of lettuce every week. So now they'll be able to grow their own lettuce through the winter and save big on that as well. So in general, these kind of projects look to be 2 to 5 years to break even on the investments, depending on the particulars of that site. And that's all we have. I wanted to leave you with my contact info. I'm very happy to answer questions by email. One of the things I love doing is helping people plan projects at any scale, whether it's backyard John Payne style or farm scale or commercial scale. Helping people come up with the right plan in the beginning is a really important first step and something that we have a lot of experience in. And it's also awesome for me to get to know people that are serious about getting real and taking better care of their nutrient cycle for their own benefit. That's about all I've got for a presentation. I am happy to answer questions. I'm trying to see, Meredith, where I can see if anyone's typed in questions yet.
There are a few here. If you can't see them, I'm happy to read them to you, but there's the questions tab that you can drop down. Can you see it, or do you need me to read them out?
I don't see it yet, but let me keep poking around. Is it in the audience view or attendees?
It's under that, so it's under audio and webcam, and there should be a bar that says questions.
Yeah, I don't see it.
Okay, let me just read them off to you.
Sure.
So the first one is from Ari, it looks like. How do you make sure the air doesn't take the route of least resistance and fresh oxygen is spread through all material?
Yeah, great question. I'm sorry, Mary, could you mute? That is the critical question that comes down to feedstock mixing. So if the material is well blended, if you have a truckload of food scraps or manure and you blend it with the right amount of wood chips or yard waste, then the airflow will work very well. It is possible for channels to develop in a pile where air flows through a channel and kind of skips other sections of the material. We haven't had that issue at all with manure-based compost systems. That's more likely to be a challenge with food scrap and wood chip blends. But the answer to that is if you've got the right mixture, then you won't have that problem. However, 3 to 4 weeks into a batch, giving that material a tumble will be another way to make sure that all the material is getting a good aeration run in terms of pathogen kill and weed seeds.
Great. The next question is, what college did you say had the dorm?
Yes, so Evergreen State College in Olympia, Washington. And I believe or at least they were planning to rebuild their Jean Pain style system this past fall. I'm not certain if they did, but I know that I've had a lot of back and forth with them as they were planning to do that. But yeah, Evergreen State College.
Okay, here's a bit of a doozy. Hi, Gaelan, Glenn from Montreal here. There was a report stating that in winter operations, when the blowers kicked in, they would lose a large amount of heat as cold air was getting pulled through the pile. The report stated that they should have dropped the height of the roof to be able to conserve some of the heat in the barn. Do you have any idea on where the sweet spot would be height-wise to allow the heat coming off the pile to stay in the barn, but not leak out of the building over time?
Yeah, great question, Glenn. Glad you could join us. That's I think one of the reasons that a lot of commercial compost sites use what's known as covers. There's a couple of different companies, or actually several, that make these tarp-style covers that go over the piles. And generally, those are used when you don't have a roof over the structure to keep rainwater out, stormwater from being an issue. But they also can be used primarily just to contain heat and help insulate. But the idea of having a fully enclosed, insulated building that the compost is in may make sense over the long term in terms of the amount of energy that you'd be able to get during winter months. The 1,000 BTUs per hour per ton that we've seen on these manure-based agri-lab systems, none of these buildings are enclosed. They have roofs over them, but no insulated walls. So really the thermal mass of the material around the outer edges and the insulating value of the concrete three-wall kind of setup is all that's really insulating them now. So what ends up happening is the outer foot of material gets cooled off as cold air is brought through it. But in the systems we've been doing, if you measure 12 inches into the pile, you're at 140 degrees. So the winter temperatures don't usually cool the piles down except for the outer edges. However, last week when we had that 25 below stretch for a couple days, the pile at Vermont Compost did cool off, at least the outer 2 feet. And that was a heavy bark mulch food scrap blend of material. So it depends what kind of material you're dealing with. At this point, I wouldn't say it's worth having a fully insulated building. Um, However, there are people that are doing this mostly to make sure they're containing odors. So maybe that's not the best complete answer, but I think it's not necessary to think about fully insulating or having a very low ceiling. You need to be able to get equipment in and out, um, and I think there's several ways that it can be approached.
Great. Next question. Will there be any fogging in the building in the winter since the fans are cycling, or since one pile aerates, then shuts down, and the next pile heats, it avoids fogging? Sorry, there were some typos in that one.
Sure. Well, yeah, you still have some steam coming off the piles, but in general, we're pulling air down through the pile. So most of the steam and moisture that would otherwise go up is getting pulled down through the aeration pipes, and most of that moisture condenses in the heat exchanger. Um, but yes, there's still a high likelihood that you'd have, if the compost is done in an enclosed building, you would definitely will have moisture on the inside of any windows or, non-insulated walls in that building. And that's not necessarily a problem. In some ways, that's an advantage because you are containing some of the moisture that the compost wants to have. Once the compost gets below 40% humidity, the microbes can go into a stall period. And if that happens before you've had a good 6 to 8 weeks of active aeration, the compost isn't quite ready yet. And you don't have necessarily a high quality finished product. So That's one of the reasons that reintroducing moisture from the aeration system that condenses back onto the pile is a method that we usually look at, because managing moisture is probably a close second in terms of variables that can be tricky, depending on your feedstock.
Okay, do you know whether and/or how the quality of the end product compost from active and passive aerated compost differs?
Yeah, great question. I think one of the biggest challenges from turned windrow and mechanical tumbling compost is that you're getting a good mix. Materials constantly being blended, so it's ensuring in some ways that you're getting everything through a hot phase that'll kill seeds and pathogens. However, the mechanical tumbling aeration method, usually 2 to 3 days later, it starts to go anaerobic, and so you're maybe turning it once a week, but 3 of those days the material is not really being aerated, so you're losing time. When you're using fans with aerated static piles, you're pretty much assured that the material is all getting very well aerated regularly. And one of the other really interesting aspects of this is that depending on who you ask, what's the ideal temperature for your compost pile? Some people like to run their piles really hot because that makes the compost process quicker. 150, 160-degree piles will generally be a quicker process than 130-degree piles. However, you're also cooking away a lot of the carbon that at that higher temperature that's getting converted into carbon dioxide, which would otherwise stay in the material and be a good organic matter for the compost. And at higher temps, like 150, 160 degrees, that's too hot for a lot of the beneficial fungal elements that will naturally develop in compost at lower temperatures. So one of the reasons Carl Hammer of Vermont Compost likes our system is it gives him the ability to control the temperature of the piles by fine-tuning the aeration timing cycles so that the piles are always in that 135-degree range. And maybe once the PFRP has been met, he can cool them down even more to the 120-degree range, which will generally mean it's a longer time process before the material is fully composted, but he is retaining valuable carbon in the compost as well as valuable fungal and microbial nutrients that come from that.
All right. We're moving through here. Glenn asks, for a commercial application, if you wanted to provide radiant heat to another building, what distances are we talking about that would make economical sense?
Sure, great question. Generally, for every 100 feet of insulated pipe, you lose 1 degree. So we tell people usually that 500 feet is about as far as you would want to go, not so much because you're losing 5 degrees of temperature, which isn't that bad. If you have a 130-degree water tank, 500 feet later, that water is 125 degrees when it comes into your radiant floor heating system, which is perfect. However, the cost of long insulated pipe runs is another factor. If you count the cost of digging that trench and the insulated pipes, you might be looking at $20 or $30 per foot. So that's another, cost factor to consider. But it's surprising, with moving water in well-insulated below-ground pipes, you don't get that much heat loss. So, in essence, you could go 1,000 feet away and it could still make, good economic sense. Closer the better, obviously, but given that, compost productions take space and people have aesthetic concerns sometimes around odors or just proximity to materials being loaded and mixed, to have the building or the greenhouse that's receiving that hot water be 500 or 1,000 feet away may make sense in some cases, just for those other reasons. But so it is feasible, and you lose about a degree for every 100 feet of travel.
Okay, Galen, Andrea is asking if you are willing to make the cost spreadsheet available for use.
Sure. Yeah, I can send that as an email. If anyone wants to just, Andrea has got my email, so she can just send me a reminder if I don't remember to send her that this afternoon.
Okay, I'm gonna follow up too afterwards and just get all the appropriate links for videos and stuff so we can try to grab that from you as well and make it available online.
Great.
The next question is at the beginning of the presentation, you mentioned a standards entity related to compost, and Pablo is asking if you can name it again.
PFRP is the acronym, and that stands for Process for Further Reduction of Pathogens. And that's just an industry standard. I believe in the U.S. and Canada, at least, Pablo's from Argentina, I believe, if I'm thinking of the right Pablo. But the basic specification is that your pile temperature is above 132 Fahrenheit for, I believe it's only 5 days, but I generally tell people for a week. And that will ensure that you've killed the vast majority of pathogens as well as weed seeds to make a good quality compost product.
Okay, great. Next question. Is there an alternative to PEX tubing which has a high R value?
Well, polyethylene tubing, the black water lines that are typically used from wells to household plumbing, is another material that can be used. It's about the same price. I think PEX might even be cheaper now. Poly tubing comes in lots of different thicknesses and grades depending on the pressure of the water inside and how high that pressure is. Um, it's not the kind of thing you would want to use if you're going to use the hot water for cooking. There's definitely a likelihood of some leach material or plastic kind of, at least I would be skeptical about that. Whereas PEX tubing, there's types that are rated for high heat that don't degrade over time. Poly tubing also lasts a long time. The best piping for heat exchange would be something metallic. Um, However, other than stainless steel and aluminum, copper is not a good pipe to use in any kind of proximity to compost. The volatile organic compounds in compost will degrade copper very quickly. Um, so stainless steel is an option, but it's very expensive and very difficult to handle in terms of the Jean Pain method. There is a version of PEX tubing that's wrapped in aluminum that's used in industrial high-strength applications where it holds its shape and has good thermal conductivity, but it's really, really expensive. So I, at this point, would say the types of PEX that are used in radiant floor heating systems are still the best thing to use for Jean Pain style systems.
Okay, Heiner's asking if compost quality is influenced by air.
Yes, airflow, I mean, really the aeration is the key critical factor to make sure that you keep the microbes happy and generating heat and breaking down the material. If you don't have good airflow, you won't have high temperatures in the pile, and you'll have a very slow anaerobic decomposition process, which generates sulfurous gases and methane and other obnoxious odors, as well as a lack of pathogen kill. So really the airflow is critical. The volume of air per ton of material per hour ranges anywhere from 2 cubic feet to 20 cubic feet per hour per ton, depending on the cycle and where the material is at in terms of its breakdown level.
So that kind of relates to the next question. Pablo's asking what the recommended airflow for negative aeration is related to the size of the pile. Is that something you can?
Yeah. I think we generally start in the 4 to 10 cubic feet per minute per ton. It does depend on the material. So if you've got a very wet, heavy, very, very heavy manure centric pile that maybe doesn't have enough wood chips or yard waste blended in, you would need a higher flow rate to get the air to move through the material. If you're using a forest residue as the main feedstock that has very little heavy, wet, food waste or manure, then you could go with, the other end of the spectrum, 1 cubic feet per minute per ton.
Okay. Further from Pablo, is there a minimum water column pressure the fan must handle so as to drive the air in the pile?
Yes, there is, and that really is getting into. I wish I was an engineer, but I'm not quite yet. I don't have that in offhand, but Pablo, I'm happy to get you some more detail on that by email. I do need to check with my engineer. That's the stuff he's always talking about in terms of measuring the water columns of pressure through the aeration system, which has a lot of variables depending on the density and moisture content and volume of the feedstock.
Okay, this next question is from David Size, and it's more of a general composting question, it seems, but it's asking what can you do if you have a lot of chicken litter and not much carbon?
Yeah, that's a good question. I think maybe another variable with chicken litter is it's I think a lot drier than most animal manures. So a process to introduce water and yard waste um, into that material would probably be the general starting point. However, the easy way to test would be to just do a batch and see what happens. You know, the moisture content I think will be the bigger factor than the carbon. You know, the bedding material that may already be part of the chicken litter could be enough. And you know, chicken litter is in some cases very dense and caked. So I think bigger factors are making sure there's enough moisture and making sure that it's been blended and broken up so that you don't have these big, heavy cakes of material that have a hard time getting air to flow through them. But one of the actually Bruce Fulford, that project in Cape Cod, the New Alchemy Institute, chicken litter was his main feedstock, and he says that that's the hottest manure material as far as compost systems. He's done everything from horse manure. He says chicken, then horse, then cow manure are kind of his top three in terms of heat. And we're about to do a project with him in Boston um, for a commercial compost site that he operates. I don't know if there's any chicken litter in that feedstock supply chain, but the good thing about these kind of questions is they're easy to test, and within a week you can tell what's going on as far as heat and moisture content and the other variables that can be adjusted either through aeration or moisture or changing the recipe.
Okay, the next question is, does covering a pile or having it indoors have an impact on the process because of certain types of bacteria which need sunlight for creating essential food sources for other bacteria deeper in the pile?
That's a great question. Not that I know of, but that's a good question. I'm thinking about who I would probably ask Bruce Fulford about that. He's been doing this for, well, or Carl Hammer. I don't know that there is a big difference in terms of what the sun is doing relative to the microbes. You know, most of the active microbes are what's going on inside the pile. The outer edges are where you don't really have a thermophilic process going because there isn't thermal mass around them to keep them hot, and the outer edges are usually dried out. So usually that's why you do a couple of times during the 6 to 10 week aeration process where you will want to turn the pile and mix the outer edges into the inside so you've got all the material with some time being in that hot um, zone, so to speak.
Okay, David's asking, have you ever built in a source to add water in the static?
Yeah, actually, well, the system at Vermont Compost, you know, the exhaust after the heat exchanger of the aeration system is going back into perforated pipes that are buried about a foot down in the top of the pile, so that moisture will get uh, reintroduced to the top of the pile and then get pulled down into the rest through the negative pressure of the aeration system. Um, Depending on your types of material, you know, the other ways to think about that would be either some kind of a sprinkler system, if you really wanted to get fancy and semi-automatic, or the idea of laying some kind of a drip-style irrigation line on top of the pile that you can potentially set up on an automatic timer or you know some kind of a logic where you're measuring the humidity of the material and you give it a burst of water as needed. One of the benefits of negative aeration is if you add water to the top of the pile, you are in essence going to kind of see that fall down through the material, and the airflow will encourage that moisture to fall down through and get distributed through the material as well.
Okay, Steve in Kentucky is asking, how do you manage a large biothermic compost pile for PFRPs and finished quality compost when a few tons of fresh food scraps are coming onto the site every week and needing immediate incorporation?
Yeah, so that's a great question. What's often done is if someone's operating on a batch kind of rotation, then when fresh material comes in, you would immediately just cover it in a layer of wood chips or yard waste to act as a temporary odor kind of filter, a temporary biofilter on top of the material. That'll keep birds off the material and keep odors from being an issue. And it won't be actively composting until you fully blend it and get it into an aeration process. That's a good kind of week-to-week cycle, and maybe once a week you load up either a new empty aeration channel or build a new windrow with the materials that you've built up through the week. But in terms of making sure that your receiving area for food waste is not a nightmare from an odors and neighbors' complaints point of view, you can either cover it in a thick layer, 6 to 8 inches of wood chips as it comes in, or you can immediately blend it with your carbon bulking agents like yard waste or forest residues, and either do a windrow kind of first version to allow some passive aeration to get going, or immediately, on a daily basis, get a new small aerated channel going. So one of the things we help people plan is their volume and sort of frequency of feedstock arrivals, and it's hard to plan. That's one of the biggest tricks with any commercial compost site. How many tons of food waste or rotten apples or brewery waste am I going to be getting per day in 2 years, and what kind of aeration system do I want to set up to allow a continuous flow? I don't think there's a single answer to how to best manage that, but in terms of ways to manage receiving area and materials and prevent odors from being a problem until you can get it blended and into an aeration process, that cover method using wood chips or bark mulch or yard waste as the temporary cover is what I know a lot of people do.
Okay, Pablo's asking, why do you use a special gas in the isobar heat exchanger instead of simple water?
Because this is a lower temp. If the isobars contained water, the temperature hitting them would have to be in the boiling point, around 210 degrees Fahrenheit for that vapor condensation cycle to happen in the tubes. The refrigerant boils at a very low temperature, and it's an almost instant process. In some ways, it's similar to a heat pump in terms of the internal solvents or refrigerants in a heat pump do a similar thing, where they boil at lower temperatures and move energy from one side of the system to the other. There's a lot of different types of refrigerants that can be used in these kind of isobar heat exchange types of systems. Some refrigerants are much more environmentally friendly and easy to deal with than others. I'm not an expert on all the different options there, but I know that there's a pretty big range. And the isobar heat exchange method itself has been around for about 60 years, and it's often used in industrial factories to passively move heat from one side of an assembly line or automotive factory to another, so that waste heat from a generator is brought back to another point where they need that heat. So it's a very well established process. The isobar is just a trademark name for these kind of shell-and-shell tubes with refrigerant in between each shell, but it's a fairly common heat exchange method.
Okay, I'm skipping ahead to this question. We've got quite a few more, and we've only got 5 minutes left. So I will be sure to send all the remaining questions to Gaelan so he can address them via email. I think we can access the specific askers' email addresses and get you an answer. But a
Great.
couple people have asked you to address antibiotics in manure and whether it poses a problem in actively aerated composting.
It doesn't really seem, at least we haven't come across any examples where, like the UNH project is an organic dairy farm. The others are not. And we haven't seen any difference in terms of the thermophilic activity of the piles. The nutrients and quality of the compost and residuals in the compost from one type of operation to the next, I'm sure there are some differences. There's been a lot of issues with persistent herbicides, particularly in horse manure that's composted, and there's some people working on ways to amend composted horse manure actually using wood ash, which in some unknown way attracts and kind of binds persistent herbicides away from the compost, so you don't have issues when you're growing vegetables with this kind of compost. But in terms of antibiotics, we haven't seen any academic or in-market evidence that there's any thermophilic compost barriers from antibiotics being present in the manure. I'm sure there are a wide range of valid questions and unknown, unresearched kinds of questions around the quality of compost. I have lots of questions about that from a human manure compost point of view, all the residuals, not just antibiotics, but all the other pharmaceuticals and other things that we bring in that the animals are also bringing in through the water. There's a pretty long list of those kinds of questions that I haven't found anybody in academia yet, at least, that's done that kind of research. So that's a really good question in general, but in terms of thermophilic composting, not really an issue.
Okay, we have a question from Sam. Can an already existing positive aeration composting system be easily changed to a negative aeration static composting system?
Yes. The only question really is where to retrofit some condensate and leachate traps to collect water that will build up in the pipes when you switch to negative. Depending on the types of pipe that you're using, or if you've got precast aeration channels, there may need to be a few slight modifications. And it's also possible that the fan might need to be a higher horsepower for negative aeration. But in general, it's very easy to make that kind of retrofit. And a lot of the positive aeration systems out there have covers, Gore-Tex, Compost, other types of fabrics that cover the windrow to contain moisture and heat. Those kinds of covers work very well with negative aeration. There's no real, and they do add some benefits in terms of controlling variables. So yeah, converting from positive to negative is mostly a little retrofit on the plumbing to make sure you can collect the condensate moisture, but that's about it.
Okay, I'm going to try to squeeze in one more. So Glenn is saying that you mentioned negative aeration producing more leachate, and he's wondering if you get the right recipe and 60% moisture content, if you have any idea how many gallons are extracted per ton on material composted. And then he cites the UNH report and their 1,500 gallon leachate tank and is wondering how long it would take to fill such a tank. So there's kind of two questions there.
Yeah, that's a great. I cannot remember what the gallons per ton per hour ranges. It does range, depending on feedstock and your starting point in terms of moisture content. But I can research that and chat with my engineer because we've been collecting that data both from UNH as well as a couple of the other projects. So I can get you that, Glenn. I just don't have that handy at the moment.
Okay, and then finally, we had an attendee, Heiner from Germany, who's got some experience with this and has cited that he did have some issues with antibiotics in manure and chlorine in water. And I've provided his information for you, Gaelan, in the organizer's chat window, in case you want to touch base with him and learn from him about that.
Yeah, that's great. Heiner was in Vermont and New Hampshire, I think, last summer on his tour across North America, and I almost made it to his workshop. I've been in touch with lots of people and glad to finally be directly connected. So I would love to collaborate with you, Heiner. I know we're doing a lot of parallel path on this stuff, and the way you've been approaching these projects, I think, has a lot of similarities to the ways we've been doing it, and would love to work together. So glad to make that connection. I will get your Skype. Okay, I see that. I'll send. Did he put his email in here? I don't see your email address. I'd love to have that too, but thank you.
Yes, we should be able to access the email through the webinar attendee list. And I just want to, we're right at 2:30 and we're out of questions. So I just want to say thank you to you, Gaelan, and to everyone for attending. We're going to try to make as many links and resources available at livingwebfarms.org after the fact. And we are very much looking at bringing Gaelan to our farm in Mills River, North Carolina for a more in-depth in-person workshop sometime in the future. So thank you, Gaelan.
Yes, thank you, Meredith, for making this happen, and looking forward to working together and seeing how we can get more people putting compost to work for them.
Awesome. Sounds great.
All right, bye-bye. Have a great day.